welcome back to the day 4 for the courses. So this morning, Dr. Aranya already explained to you what is the microwave pyrolysis to produce the bio oil. And after that, it's upgraded into the biodiesel through other process. So this section, I would like to discuss a little bit more about the sustainable aviation fuel. So, what you understand about sustainable aviation fuel? Why we call the sustainable aviation fuel instead of maybe the biofuel or biojet fuel? So, what is the difference between the sustainable aviation fuel and also the biojet fuel and also the biofuel? What is the main difference? So, yeah. In these courses, I would like to discuss what is the challenges that we are facing when we want to develop the sustainable aviation fuel, and also what is the perspective and also the future for the sustainable aviation fuels. So you see, by looking at the word sustainable fuel, must be overall process, must be sustainable. So when we talk about the biofuel, biofuel, yes, is from the organic materials, but sometimes and during the production process, it will emit a lot of the harmful gas, for example, like the CO and also the CO2. So that's why I make it not sustainable. So the word sustainable here is the what? To make sure during the production process also must be green. Must be green. So that's why they use the word sustainable aviation fuel, which is different from the biofuel. Yes, sustainable aviation fuel is one type of the biofuel as well, which is more cleaner, without emit any emissions during the process as well. Because normally when we use the biofuel, we look at the consumption part, which yes, indeed the biofuel will emit less emission. Harmful emission like the CO2, CO during the combustion, during the consumption. However, during the process, maybe they use a lot of chemicals. So during the process, the energy input is maybe the highest, and also the emitted the CO and also the CO2. That is the thing. So why sustainable aviation fuel is important? Because the airline already committed to reduce the total net emission to half level by 2050, compared to the 2005. So in order to achieve this one, because it seems like it's impossible, because why? The air transport is increasing year by year, beside the 2 years during the COVID times, but it's increasing, almost double, triple for every 10 years, double for every 10 years. But how to achieve it to cut into the half by 2025? So they have the phase by phase strategies. First, the ICAO, which is the International Civil Aviation Organization. They established one benchmark, one policy, which is they call it COSHA, which is the carbon offsetting and deduction scheme for international aviation. So throughout this, maybe it might be possible. Later I'll tell you more what about it. This one is a very important step in order to achieve the direction, which is to reduce the overall emission from the airline to half or even to net zero, totally net zero throughout this. And this one is what? To enable the carbon neutral growth. The carbon neutral, what it means? To remain. First step, to remain first, as compared to the 2019. Not directly to reduce first, to maintain, to compare to 2019. So this is the very initial steps, which most of the country around, I don't know how many country, this mentioned here is 60%. Some of country already committed this policy, which starting from this year, they plan to implement 1%. I think many countries will be planning because they are not enough demand. So that is the perspective of the sustainable aviation fuel. Demand is what? What is the problem? Later I will tell you. So in demand, so they expect to increase the overall participant country with the large economy like the China, Brazil, and India in 2027. So currently, the sustainable aviation fuel policy, regulation, and also the market mainly are from the European Union country, and just European Union country. Even though last few days I mentioned that China also increasing to producing the biojet fuel or sustainable aviation fuel to export into the European country, because they have the demand there. They have the demand there. Later I will tell you with one case study of one country. So how they suffer from this one. Suffer means what? Not because of technology, but they are unable to find a sustainable raw material, sustainable suitable raw material for the sustainable aviation fuel. That's the thing. So that's why. So during they have two states. Later on I will show you the graph that they divided into the two states with the aircraft operation with the emission greater than 10,000 tons of the CO2 need to report their emissions. That is the policy at the very beginning. This one. So see, what is the Croatia doing? Because they are the final aim. The final aim is to achieve half of the total emission is compared to 2005. Correct? This is the final aim. Then eventually hope to achieve net zero by 2050. But this one, the Croatia have the intermediate plan which they use the benchmarking in 2019 to compare with 2019 set as a baseline. For the first phase, which is the voluntary stage, which they started in 2021. Hope that over 80% of the growth of the air traffic CO2 after 2000 will be offset. So the pilot phase already done, finished. Now we are moving to the first phase. What I'm discussing here is basically happening in European country, not in Asia. In European country, this is what's happening now. So that's why the Asia will start following. So in these 2 years, we have heard a lot of the term about the sustainable aviation fuel to say, because it's initially started from the European, which they have their mandatory phase starting from 2007, which they aim to have the last economy country that will join them. So they are expected to give for some small island or least developed country, because they have one problem we are facing is what is very costly to build the sustainable aviation fuel plant for the certain country or areas. So this is what. So they have their own target, which eventually they will offset by up to 70% of the total emissions. So now that is the background. So that's why make it why the sustainable aviation fuel is important. So now we need to know what is the sustainable aviation fuel. Like that is alternative clean fuel for the aircraft. So this is to produce by using the renewable feedstock. For example, the waste oil, the agricultural residues, so that the SAF, the same, can be reduce the overall CO2 emission by up to 80% in compared to the using the fossil fuel based fuel. So just now, my question, my initial question, what is the difference between the sustainable aviation fuel? Because the biofuel basically are from the organic material, for the plant, animals, and material. However, some of the sources are from the non-biological sources, which make them not sustainable. And secondly, during the production, we will create some harmful emission that I mentioned just now. So they prefer to use the same, which is the sustainable aviation fuel instead of the biofuel. So make them different. not only we want to get the green fuel, but the process must be clean, and also the raw material, the feedstock, must be sustainable. So that's why. So normally now the sustainable aviation fuel are from the biomass feedstock with the low carbon content. So the CO2 emission during the combustion can be minimum. So one thing is very important. I also stress during the last few days. We must design a fuel that's suitable to be used for the engine. Not the other way around. After we produce the fuel, then we only design the engine. This one is not like the internal combustion engine or generator. The costs to modify the generators and also the internal combustion engine might be relatively low compared to the aircraft. If you want to design the aircraft, can cost easily. I read from the statistics around 1 million for one airplane. Easily 1 million when you want to design or modify something. So that's why. So for the sustainable aviation fuel, we need to design or produce the sustainable aviation fuel that as close possible to the for Jet Air 1 or the fossil aviation fuel. This is very important things must be designed. So what is the sustainable aviation fuel? No, what is the Jet Air 1 fuel? They are the hydrocarbons. So how we going to turn this all feedstock into just the hydrocarbons. So this is a potential pathway. So commonly there are few pathway. This one first is the Fischer-Tropsch. So for me, I like to use the second method, which is using the oil directly. One step oil based or the ester based or the fatty acid based resources. So this one is the second method. So there are many methods. So currently throughout this method they already test. So some of the method can blend up to 50%. Can blend up to 50%. That means what? Can blend up to 50%. Still, they can fulfill the ASTM standard. They have a certain. I show you or not? I didn't show you. Yeah, they have a certain ASTM standard they need to follow and or fulfill. So currently, blend up to 50% by using the Fischer-Tropsch hydropress synthesis. Maybe can blend up to 50%. So this is the potential feedstock, biomass feedstock from the wood residue or municipal solid waste. Then this is a process that I like to use, which is also from the hydropress, but my raw material are from the ester or the oil base or the fatty acid base material, which they come from the used cooking oil, which currently the market is produce the sustainable aviation fuel is from the used cooking oil because we can get sustainable materials. Then animal fat or algae. This one also can blend up to the 50%. So another method is using the micro conversion of the hydrocarbon from the sugar. This one is from the sugar directly. Hydropressing of fermented sugar. So this one can blend up to 10% due to the current regulations. Another method, this one is desynthesize corrosion with the aromatics derived alkane of the light aromatics from what? From the municipal waste or from the forestry residues. Another one, this one is from alcohol directly. This one is much more simple process, but they need to convert it into the alcohol first. Alcohol to the jet. Alcohol to the jet. Yes.
You can do sugar already carbohydrate based feedstock to ethanol,
alcohol.
Ethanol
to jet. Yeah. Correct. So later on I will show you for the each pathway. They still have a lot of the step, you see. That is the potential step. So the last one is the catalytics of the hydrothermolysis of the jet fuel, which this one also from the plant oil, soya oil, waste oil, algae oil, and this one the blending also can up to the 50%. 50%. So this is the potential pathway to produce the sustainable aviation fuel.
Which one is the least complex among these?
No, all is not to say very complicated. All are the very complicated. Then they have their own challenges and also their own advantage. And also, different pathway they using the different raw materials. Then some of pathway they need to go through a few steps. 1 step, 2 steps, 3 steps. Some is directly 1 step.
So
Yeah.
which one is that?
What?
Minimum steps.
Minimum step can be the single step. Single step you also need to depend on the raw material. So for me, I use the hydropressing the single step. Later I show you the difference between you see here. Here, they use the what? 1 step, 2 step, 3 step. From the different techniques, from the different techniques different raw material. So nothing wrong and nothing right, nothing wrong and nothing right. So must be much more easier, because sometimes 3 steps is what you know. After you convert, you can get more pure sustainable aviation fuel. That's the thing. Much more easy for you to convert. But single step facing the challenges. So maybe the overall yield might be relatively low. So how you want to extract out the selectivities? Yeah. So then this one in more detail. So this is on more scientific part, which to produce biojet fuel. Similarly, we have produced from the alcohol to jet, gas to jet, and also the oil to jet and sugar to jet that I show you. This one I recategorize. So for the each process, they have their own method. For example, alcohol to jet. So this is the process. Gas to jet. That is the process, and so on and so forth. Which in our study, we are using the oil to gas, which we are using the hydropressing. So for the hydropressing also, you have the 1 step, 2 step, or 3 step. Not necessarily the single step. 1 step, 2 step, and 3 step. You see, for the hydropressing process, these all reaction took place. These all reaction took place. Then these all reaction will produce what you know. Some reaction will produce the CO. Some reaction will produce the CO2. So that's why I call my product is just the biojet fuel. I didn't call the sustainable aviation fuel. The biojet fuel, yes, my product is already bioproduct. But during the process, CO2, CO will be produced. That's the thing. So how to make sure, how to minimize the CO during the process, this is what you need to consider. That's the thing. So that to meet the requirement of the sustainable aviation fuel. Not only to meet the property of the jet airline fuel only. That's the thing. To make sure. So of course, for the fuel property, they have a certain STS. If not mistaken, it's 16 something already. They have the standard. If you Google, you can get it easily. What is the standard that you need to fulfill? You see, this one from this process, they are the many other steps, the cracking, and also the separations, using the distillation. Then to get your biojet fuel or green diesel or nectar or the light gas, because these all will be produced as a byproduct. So some people they produce the green diesel. Green diesel is very close to what? Close to the jet fuel already, biojet fuel, the sustainable fuel. Yeah, that's the further step. You can upgrade into the jet fuel. The selectivity is almost overlaps. The selectivity is almost overlaps. So yeah, biojet fuel. So this is the potential selectivity. That means the compound what we produce during the biojet fuel. Isoparaffin, paraffin, alkanes, isoalkane, and the olefin and aromatic compound. So that is the existing market, existing market and capacity. You see, like what I mentioned. So normally now the market, the production front are from the what? From the European and US only. So China and I mentioned is starting already. China and Singapore. In Malaysia only the China and Singapore. Yeah, I know. India also starting already. They announced they want to have a certain policy and build sustainable development plan. Yeah. So you see the market. You see the production. The total production capacity is relatively small. You see why I say small? Only 800 kilotons per year only. So relatively small compared to the demand. Because currently the overall productions only can accumulate less than 1% of the total needed of the jet fuel. Yeah, less than 1%. Less than 1%. Less than 1%. So there are a lot of the opportunities. This is what I can tell you. A lot of opportunities and a lot of challenges as well. So it's a total renewable. Yeah, you see. Yeah, you see. This one still divided into the two parts. You know, one is the total sustainable fuel. Is the total renewable reserve only. Yeah, renewable reserve only. Not really sustainable. That's the thing. Renewable reserve, and some is a total sustainable fuel. So they have the very strict requirement for the sustainable aviation fuel. That's why I make it different. Not only you able to produce the biojet fuel, but make sure the overall process is not they will categorize because they have the certain certificate agencies, certified agency. They are certified whether your process is totally clean or not, or whether your product is fulfill the requirement or not. Yeah, they have the certified. So yeah, this one is the current market that are facing. I take the example is in UK. In last year, you see total 141 million liters of the sustainable fuel has been applied. So you see it increased almost double. I mean we 45% increase in 2000 compared to the 2033. But 45% of the fuel sources are from the 0.4. Only 0.4 of the total are from the used cooking oil. So they are urgent to have the reliable sources. You see, because in UK they aim to have the how many percent? 1% or 2%? Yeah, 2%. The total amount that they need is what? 230 million liters. They only can produce 141 liters only. They want to have the around 2% to meet by 2025. 2025. But they able to meet 0.4% from the used cooking oil. So that's why it's very important to find sustainable sources or sustainable and reliable sources for the sustainable aviation fuel, because they already committed to have at least 2% by 2025. Then the challenge is what? To create a commercial scale of the sustainable aviation fuel production is need a billion of pounds. This one is UK scenario. A billion of pounds of investment. Yep. So they are also concerned of the supply. Supply wouldn't be able to keep up the demand. The supply of what? Supply of you see there are two main problems here. First is what? Very huge initial investment cost. Second thing, we are unable to find sustainable sources. Yeah, sustainable sources. That's the thing. Yep. So if they want to increase by 10%, they need 1.5 billion liters by 2030. Because they already projected. So yeah, that's the thing facing by the current market. So this is the brief instruction there about the sustainable aviation fuel. Then now I want to move on to the what our study. In this study, we want to determine what is the most optimum for this study. Is the exponential study or the very fundamental study to find the raw material that available in Southeast Asia. I can say it's a tropical country, meaning in Southeast Asia country, and what is the potential pathway that can produce the biojet fuel. I didn't say the sustainable fuel first. So to get the biojet fuel, so we tried a lot of feedstock, a lot of the commercial catalyst without modifying the catalyst. But the second phase, we will identify what is the sustainable raw material or the resources that we can use. Then what is the targeted process and targeted catalyst can be used so that it can reduce the overall CO2 and CO during the process, and to get the qualities biojet fuel. So in this study, we want to see what is the effect of the different commercial catalyst, the effect of the catalyst rolling reusability. This one more on catalyst activities. The second is to determine what is the optimum the jet fuel hydrocarbon based on the palm-based feedstock with the different fatty acid profile. The fatty acid profile will affect the end product because I think last few days I mentioned to you they need the shorter carbon change because the DSC profile can let you know what is the carbon change of the raw materials, and to determine what is the proper burning ratio of our product in order to meet the ASTM standard or the ZA1 specifications because we want to produce the biojet fuel as close possible to the ZA1 fuel. Then lastly, we also do some preliminary study. What is the soot particles and also the particle size distribution of the different biojet fuel that we produce and brand. Whether it really can reduce the emissions or not, can reduce the soot particle or not, the particle size can be reduced or not. This one, we do some preliminary studies about that. So based on the digital study, then we found that these fields, these field properties might be these field parameters might be affect the process of biojet fuel production. So that's why we are focused on what is the type of the catalyst using, the type of the catalyst, and what is the type of the raw material, the feedstock we are using. Then see what is the burning ratios, the maximum burning ratios with the commercial jet fuel. Commercial jet fuel, we are choosing the ZA1 fuel so that it still can fulfill the biojet fuel requirements. So this is our scope. So we identified few very common catalysts, 5 types of the catalyst with the loading, various percentage of loading. Then the catalyst reusability up to 5 cycles, and see what is the effect. Then the feedstock, we identified for 3 feedstock. 3 feedstock is also related to palm oil because Malaysia we produce a lot of palm oil. One is the used cooking oil, but palm oil based used cooking oil. Then palm kernel and palm orange oil. So we particularly see whether which one is more suitable, because we really need to see what is the suitable selectivity, and the blending ratios we went from the 20 to 100%, with increase of every 20%. So for the fuel properties, we look at the chemical compositions by analyze using the GCMS, and the low temperature, fluidity and combustion characteristics, volatile, and also the lubricity of the fuel properties after that we produce. Then another quantification study is the soot particle size. We need to know what is the soot particle size. So this is the comparison, because before we conduct, we need to do to compare. with other studies. So this study we conduct in 2018. So that's why there are no any. So there are more studies already appear here. So you see, just now I mentioned by using the hydropressing, we are using the hydropressing method. Hydropressing methods are from the oil-based or the fatty acid-based raw materials. So by comparing these all criteria of production, so they some study they using a 1-step, 2-step, or even the 3 steps. Nothing wrong and right. 1 step, 2 step, and also the 3 steps. So we choose to produced by the 1 step. So normally people for the 1 step they using the deoxygenation or hydrodeoxygenation process with the hydrogen, or some of the study they are using the pyrolysis or even the co-pyrolysis. This one co-pyrolysis mix between the bamboo waste and also the microalgae. So they are able to produce the biojet fuel. So currently, the biojet fuel that produced is relatively low yield. This one is not. This one is the biojet fuel yield, and not consider the selectivity yet. Not consider the selectivity yet. So there are a lot of studies about the hydrodeoxygenation process and also deoxygenation process. So they are using the mono compound. They are using the mono compound to see whether they can produce the green diesel or not, the green diesel or not, or jet fuel. Jet fuel I mean the jet selectivity or not. From what compound they can produce what type of the jet selectivity. So but what we select here for our disease study only using feedstock directly. Yeah, the mono compound is good for us to prefer whether we have this fatty acid. So what is the potential pathway to convert into oil? What is the potential reactions that can have if we have a certain reaction? Yeah. But if we are using the feedstock, so there are many different compositions. So we don't know what pathway what we follow. So that's why some of the feedstock they have very long chain of the hydrocarbon. I mean the carbon chain. So at the end we might get the heavy, I can say the heavy biojet fuel, which the total density might be higher. So this is some comparison. So our step is what prepare the feedstock and catalyst. You should set up the experiment, do the characterization, analysis of result and conclusion. This one quite common. So this one, we are using the hydrodeoxygenation process without the pressure first. So this one is the fatty acid profile of the feedstock. Analyze the this one to analyze. This is not to produce the jet fuel first yet. This one to analyze what is the fatty acid composition. Sorry. To identify what is the fatty acid composition, we need to know what is the number of the carbon chain. So after that, we activated the catalyst. So the reading here is we refer to the literature based on what is the optimization catalyst activation condition. We just use that follow its condition. So because we want to just see what is the potential step. Yeah, this is the jet fuel production. So our aim is to explore and also figure out what is the potential feedstock. So we want to identify three best catalysts because we are using 5. Then aim to define 2 best pairing. Pairing is what we have 4 feedstock and 5 catalyst which pair will produce the highest selectivity of the biojet fuel. Then after that we will find the different catalyst loadings and also the brandings and also the reusability of the catalyst. You see of the catalyst. So we are using the nitrogen gas. This one is a condenser. So what we didn't measure here is the what? The waste gas. The waste gas we believe will produce some CO2 and CO because the profit we follow the CO and the CO2 will be produced because we are using the hydropressing process. You see the process we are using is what? This one deoxygenation. This one decarborization. These two process, the first two process is what we are using. So if we have the fatty acids plus the reaction, after the reaction, the jet selectivity will produce at the same time CO and CO2 will produce. So we believe that the CO and the CO2 is produced during the process even we didn't measure. And after that, we will do the characterizations. As I mentioned, we are using the GCMS to measure what is the potential profile, and also the selectivity, profile and selectivity, and to measure the viscosity. Viscosity is very important for the biojet fuel or the biofuel. And the other properties. And lastly, we also measure the rubicities and also the truth diameter to see what is the potential emissions will be produced by using the biojet fuel. So after that is the analysis of the result. Okay, so yeah, I need to make it clear that the mass here that we obtain here is what? The total product. The total product of all the product. Liquid product here is what? We only select the jet hydrocarbon only. The jet hydrocarbon. So jet hydrocarbon. Then the jet paraffin selectivity is we just select the C between C8 until C16 only. So we measure these two things because we need to make sure what is the component of compound after we produce. So we not just take the total mass here because total mass here is not fair because some they have other impurity profile. So we just see what is the jet paraffin selectivity or the liquid product here. Yeah. So yeah, this is the first set of the experiment. You see, this is the compound that we produce. This is the compound that we produce. We have the N-paraffin, isoparaffin, olefin, and this is all the what? The jet fuel selectivity. The jet fuel selectivity. But here we don't know what is the carbon chain yet because sometimes the carbon chain might be more than 16. 16. But this one is all the jet selectivity. Jet fuel selectivity. So this one make it what? Make it the composition in the liquid product. This one we just focus on jet selectivity. This one you see the total jet selectivity that produced is 60%, 50%, 50 over percent. Which the composition we have the N-paraffin and also the isoparaffin, olefin, and aromatic compound. We also divide sort out the carbon that we have more than C16, yeah, the carbon more than 16. No, this one is a total mass. This is a total. This one is total. Yeah, this one is a total. So you see the WCO is with waste cooking oil, but with brand name is what? Without any catalyst. This one WCO with 5 types of the catalyst. So we found that they are the low catalyst activities. Effect of the catalyst, or want to see the effect of catalyst. So this one we found that they are low catalyst activities by the basic catalyst of the CaO and also the titanium oxides due to the cake will be formed. This one the cake will be formed. And the zollite, vanadium, and also the barium carbon catalysts are the potentials to enhance the production of the jet fuel. Which one? Or this one has the higher vanadium. this one without, this one without. Then the, oh yeah, the mass is highest, the highest one. And they also have the highest end paraffin, highest end paraffin. So these three, 1, 2, 3, these three are selected. So now we further study that the effect of the different type of the pump-based feedstock, which we have the waste cooking oil. This one waste cooking oil is a pump-based used cooking oil or waste cooking oil, pump kernels, and this one is a pump olefin oil with different type of the catalyst. Compared with catalyst and without the catalyst. So we found that this one, the pump kernel oil, with the vanadium carbons and also the vanadium oxides, have a fair amount of the paraffin. We maintain the low olefin yield and high mass yield, the high mass, which is more than 70%. So the lower fatty acid derived feedstock generally reduce the chance of the olefin for undergo the hydrogenation reaction to forming the end paraffin. So yeah, one thing I need to bear in mind is, you see, what we found is we need to have the raw material or the feedstock that have the low free fatty acid. Free fatty acid will have the negative impact on the overall production. Then after that, this one is a different loading catalyst because we found that this one is the best one, so we use these two sets to further study with different loadings. We found that if the loading of the catalyst is go high, that means the total paraffin also higher, also go higher, which the total paraffin highest at the 8%. This one for the 8%. This one the paraffin. This one is almost similar. For this one is almost similar. So, yep. This one 8% is the highest for the pump kernel. By using the vanadium, both also higher. They say both also higher. With the lowest of the olefin. Yep. Then after that, we go to see what is the effect of the biofuel branding. Okay, so after that, we found that the 8% have the highest end paraffin. So we just take the 8%. The 8% one is yeah. One. Let me see. Branding, yeah. Two types of the pump kernel. I think we take the 8%, then we brand with the various percentage. And this one is a Jack 100%. This one is a Jack A. This one is a 100%. Yeah, this one is a 100%. 100% Jack fuel. And this one is 100% Jack fuel. So this one with branding. With branding with different percentage. Different percentage. So we found that branding at 20%. So the highest amount of the liquid product and lower olefins. Lowest olefin. So we take the 20% to further analyze the properties, the various properties. You see the first property we analyze is what the density. You see we draw the two line here. Two line here is the SDN standard for the jet fuel. For the jet fuel, which must be the density must be lower than 0.4 gram per cm cube. Cm cube must be higher than 0.75 gram per cm cube. So with all the branding, this one is a brand. let me see which one is the branding of it. Oh, this one branding with the this one is the pure pure ZA1. So we have the two type of the biojet fuel. One is the using the palladium carbon, which is in the gray color, and also in the orange color is the vanadium oxide. So we found that most of the blending are fulfilled beside the what? Beside vanadium with pure biofuel. Biofuel. Then about the low temperature derivatives, which is the kinetic, kinetic study. Use kinetic viscosity study. So the kinetic viscosity study must be lower than I think 1 point something or 2 mm³ per second. But you see, most of it will be more than that. More than that. Just 20% is slightly higher than that. Most of it is higher than that. So only the ZA1 fuel. So that's why previously I mentioned our viscosity is still slightly higher, which is we need to still reduce it, because the viscosity, higher viscosity will increase the molecular weight as well. So, and also the high viscosity will cause the emission delay, and also will cause the negative impacts of the atomization of the fuel spray, because the viscosity is very high for that fuel. So that's why. Then this one is the freezing point. Freezing point is one of the most challenging one, because basically for any type of the biojet fuel that we produce, we have the reactivity very high freezing point. So that is the part that we need to take care when we want to produce the biojet fuel, because reactivity. But after it's blending with the ZA1 fuel, it's still up to 20% for the this one. The palladium carbon one is also slightly lower than the bar. So that's why the second properties you need to take care is what the freezing point, because for the normal biojet fuel or normal green diesel, the freezing point that required is just a -10, but for the ZA1 fuel or for the biojet fuel, you need to have the -47. It's only a -47. So yep. Then lastly is about the calorific values. The calorific value. The calorific values must be it's decreasing. Must be higher as well. So our benchmarking is around 46 or 47, 46 and 47 millijoule per kg. Millijoule per kg. What we get also slightly lower. So yep. So that's why we need to make sure you have enough energy content per unit of the biojet fuel that you produce. Lastly is about smoke point. So we found that in the biojet fuel, as I mentioned before, the biojet fuel generally has a lower smoke point compared to the fossil ZA1. So you see, this one is the ZA1, they have the highest. So basically blending with the 20%, we will have the lower smoke point, So yep, basically this one is the expected result, because why? The biofuel generally have the lower. This can be increased with the carbon, or increasing with the carbon per hydrogen atomic. Yes, correct. Because why? Because the smoke from where? From your carbon. From your carbon. Yes. 80% is more protein. It means is for the brandy.
Yes, I think second is 20%.
Yeah, correct, correct. So yeah. So we have to take the average point because for the other properties 20%. Yep. Then the lastly is the point. Fresh point normally not a problem because the fresh point normally the fresh point for the biofuel is relatively high. So the fresh point don't have any problem. Fresh point is due to what? Due to the storage and also the shipping and the transportation issue. But normally the fresh point of the biofuel is relatively high. So this is not a main issue. Main issue. So the final breaking point, the final boiling point. For boiling point is also the maximum limit we can have is 300 degrees C, but all the blendings are less than the 300. So this is not the issue also because the final boiling point is what to make sure they have the complete combustion. So no formation of any deposits during the combustion. So that's why all the blendings are including the pure up to 95%. Yeah, of the biofuel at the lower boiling point. And lastly is the rubicity. The rubicity. The rubicity is what is able to help to improve the moving part. The moving part. So we have to make sure the rubicity is up to the certain level so that the fuel pumping and also the flow rate of the fuel moving smooth. So most of the blendings including the pure biojet fuel also have the desired rubicity, which is lower than the total requirement. The maximum requirement is 850. Yep. So then lastly is about the soot emission. This one also as expected because the pure biojet fuel, the pure biofuel normally have the lower emission. Have the lower emission. Due to the incomplete combustion of the jet fuel and burnt hydrocarbon. Yeah. Then after that, we go to test the what? The reusability, usability of these two types of the catalyst. We found that we are using the 8% of the loading. We found that it's up to 5 cycles. It's five cycles. The total production. Still, I mean the reuse still higher, but if compare between the vanadium and also the vanadium oxide, which the vanadium oxide have the better reusability because why? You see, all is almost not any reduced in the total mass here. Not reduced in the total mass here. Yep. This one also same. I think both are also relatively have the similar result. They can quite stable because why? This is the one of the commercial catalysts without any modification. So they are quite stable. They are quite stable catalysts. So our main finding from this study is what? We found that these two types of the catalyst, 5% and 8%. 5% is able to make the optimum amount of the jet hydrocarbons through the deoxygenation process for the waste cooking oil. Then the vanadium oxide catalyst have the better reusability compared to the vanadium carbon because of the jet salinity of the vanadium carbon have the highest reducibility compared to the vanadium carbon. Then, but for the palm kernel oil, the liquid product can up to 99%, which they have the favorite selectivity, which is the palladium. Palladium selectivity is up to 73%. Both also 73%. Then this one also 95%. Then the acceleration of the palm kernel, is optimum at 8%, which they can achieve around 70% of the jet selectivities. For what? Paraffin selectivity for the alkanes with the least olefin. Yeah. Then for the blending of the 20% is also fulfill the standard. Besides, there are two things almost in the borderline, which is the freezing point and also the viscosity. Freezing point and viscosity. So this is very two important properties that you need to make sure is reduced, can be reduced. So this is our finding. So our question here is why the sustainable fuel are not widely used in the market yet. Because of the price. What price? What price?
Production cost is apparently little
Yeah.
higher than conventional.
First is the production cost. Like you see, the second one is the production cost. We must make sure that the overall production cost is as low as possible. At the same time, the price is what? Because the jet fuel, not necessarily any type of jet fuel is significant for the total operating cost for the airline, any airline. That's why. Because if we cannot maintain the cost of the sustainable fuel as compared to the jet airline fuel or the fossil jet fuel, so that's why it cannot be compatible to the fossil fuel. Because you see currently for the fossil fuel, it's around 600 euro per ton, but the current cost for sustainable aviation fuel is around more than 1,000 euro per ton, which is how many times higher? More than 50 times. Yeah, more than 50. More than 50. Not time percent. More than 50% higher. More than percent higher. So we need to make sure the sustainable aviation fuel must be as close as with the fossil fuel. Then one more thing is the fossil fuel. The price of fossil fuel also fluctuation. Sometimes go up, sometimes go down. If the fossil fuel go down, then how you need to make sure your sustainable fuel can be followed to go down as well. That is another challenges, Yeah, that's another challenges. That's the thing. If you see, because previously I discussed with you about the correlation between the fuel and also the food. If you're using the food sources or edible sources for the sustainable aviation fuel, if the fuel prices is decreased, fuel prices is decreased, so the farmer tend to turn the edible oil into the food, so make the overall edible oil might be increased as well. If you were to use that sources, that means the overall cost for the sustainable aviation fuel also increase. Yeah. So that's the thing. So how you need to make sure the price is compatible. So now they can achieve that through the incentive only. Because now it's an incentive because many countries they want to push for the sustainable aviation fuel. So that's what is incentive. Another one is the like you mentioned is the production cost. So how we need to make sure the overall supply chain. We have the stable supply chain which we can get the sustainable feedstock that's available and also the logistics. Because overall this sorting is not yet noted because the current sustainable fuel is heavily rely on the incentive only. Incentive. Yep, that's the thing. So yeah. Oh, this one. If you want to know, the overall production cost, you need to know what is the overall feedstock and also the pathway for any process. So because before we start any process, we want to know whether it's economically feasible or not. So before that, you need to know what is the pathway for any type of the feedstock and or any type of the process. Because later on, I will discuss about the overall life cycle cost analysis. Life cycle cost, so that's why we need to know this one. This one is the oil-based. For example, the oil-based feedstock. So you go through the hydropressing of the ester and fatty acid method. So which I'm using this method. I'm using this method. Then we also have the sugar to jet. So what is the pathway they are following? Then another pathway that currently they are using is gasification. I mean, industry are using is gasification to produce the biotech fuel. So this is a quite stable and established process already, the fuel process. So yeah. So that is the pathway. So how you going? You can do the cost analysis through the process simulation. Process simulation, because from the process simulation you can know what is the major component or utility for each process. Yeah, this one is process simulation is very important, so that you can save your time. To do the plotting. So from the process simulation, you can know what the overall material and energy balance. So if you can know this one, then you can know what is the potential operating cost. So in order for you to do the process simulation, you need to have the data input. The data input is very important through the experiment or through the what. So that's why through the process simulations or the experiment, then you can have the input. Then after that, you can simulate what is the percentage of your output, what is the potential product, and also the capital cost and operating cost, as well as what is the emission, because why we have the energy balance. We have the energy balance. So the energy balance they show very clear in the process simulation. For our group, yes. For me, for the process simulation, we use the Aspen Plus. Aspen Plus. Aspen Plus. So this one is I'm not promoting this simulation tool, but this one is very good for the industry process simulation. Industry process not only used for research, but also very useful for the industry's process simulation as well. But the license. The license, there are two types of license. License for economics is basically lower cost or affordable cost, but this license cannot be used for commercialization. Cannot use for commercialization if some company want to ask you to do the process simulation. You have that license, which on your institute got that license, but you cannot use for the company. If you get caught, your institution, and you can get a very serious fine. And this one must be yeah. It's very worried.
It's individual to each industry. It's specific. It's individually given to company.
No. If you yourself own that software, and you can do for any country, any company. If you are the consultant for that company, you own that license, you can do. Yeah, you can do.
Can you suggest any other
COMSO also another good process simulation tool. Yeah. So yeah, in our group we are using this one, but of course we are using the academic license. We didn't do for any commercialization. Commercialization has a totally different license you can do. Yeah. But this software or this tool is very good for the industry process simulation. So try to learn this one if you have time now, because why? In the future, when you work in any industry, you want to go back to industry, you want to do the consultants for any industry to improve their process. This is very useful. This is very useful. Yeah, for any industry process, you can.
For audits also, industry audits.
Yeah, industry audit. If they want to see their carbon audit or emission audit also can. Yeah. Can. Yeah. Mainly the industry is used to improve their efficiency. the improve the efficiency so that they can reduce the overall cost. Yeah. So identify. Then this is the costing. So this one is I obtained from one of the researchers from India also. He's already doing costing in Indian rupee. Yeah, then you see the overall cost is 113 per kg at this moment. 113. Then you see basically what the overall cost it comes from what? Feedstock. The feedstock cost. The OPEX and CAPEX is almost similar. For me, I also do the costing also, but for me, I do for my research. Later, I'll show you how to do this one. How to do this one. I didn't do for the jet fuel yet, but I do for method are the same. So this one I will show you my case study about that. So you see overall, feedstock normally account 70% of the overall price. So if you can able to get one reliable, sustainable with low cost raw material or feedstock, you can make it. Yeah. OPEX and CAPEX also relatively small, and they have the hydrogen. They need the hydrogen. I assume he produced using what? Using the hydrodeoxygenation process. I believe because why? The hydrogen. He input the hydrogen cost as well. So what he believe is the overall cost. So you see from here, what can you do? How can you do? You see, besides the feedstock cost, the cost of the hydrogen also relatively high as well, right? So how are you going to get the low or sustainable hydrogen production as well? That's the thing. There's two things that you can do. Then the OPEX and CAPEX also is very low cost. Yeah, this is what I told you. You see, we want to achieve net zero in 2050, right not? You want to achieve net zero. I think most of you heard this term before, net zero in 2050. So you see the emission is increasing year by year since 1990. Not to say since 1990. We have the data from 1990 because I show you before the 17th century already started the emissions. So you see it's already reached to almost how many emission achieved 1,000 million ton. Yeah, it's almost same. I show you last few days. COVID time, there are some right now. You see, if this policy is control, you see, will be increase 5,000 and ton. So, if we do with the additional, so the overall tools can be to 2,000 metric tons from 5,000. 5,000 is a business unusual from one of societies. If that can be reduced from 5,000, but if we put more efforts, we achieve the net zero. So this need to close, and this is the gap. So yeah. So because we want to have the carbon neutral in 2030, our intermediate goal. The carbon neutral, what is compared to 2005, 2000, no any increase in what in the emission, carbon neutral. That to achieve the, so that is the most we need to do. Oh, that one cannot. No. Yeah. One more round of COVID. Yeah. Here because you see the or whatever. They energy. They want the not considered because the they also talk about the sustainability, recyclers, the what, the healthcare waste. Not only health, want to make their overall system, the procurement system, all the system sustainable because the care industry is more popular in any country around the world. Yeah. So as a we already achieved so compared to 1990 achieved so much. This one without any policy, we will increase by this line. We already achieved so much. Fight today is what? Only half of the CO2 did in 1990. So all the sector of industry are working the way to reduce the fuel use and also the emission further. So any questions so far? So I have another small slide to show about the life cycle cost to show you how we going to analyze the life cycle cost. So before I continue, any yes?
In one of the slide of resulting discussion, we will mention on the soot particles.
Soot particles, yeah.
So, in this, the production of soot is enough because of incomplete combustion, but due to oxygenation, we yes, this one.
Yeah.
In the second point, we are doing oxygenation. How is it like higher particle?
This will lead to the earlier soot oxidation and higher particle rate. Aromatic. So this one, I mean, if we have the more aromatic compound, will lead to the what overall soot will be higher. So that's why this one is we based on the composition. We compare they have the high aromatic compound. So that's why they have the higher lead to the higher growth. This is your question. Your question is what? Why lead to their soot?
Even if there is oxygenation, so there must be complete combustion if there is oxygenation. Why the particles?
No. Soot happen is incomplete combustion. Right? Soot is not the CO2. Soot is is incomplete combustion. Your question is what?
If
What?
we are doing oxygenation,
Oxidation.
combustion.
Yes.
So what is the meaning of the higher particle growth rate?
Higher particle.
How is it related to oxygenation?
Will lead to the earlier soot oxidation and higher particle growth. This one I don't know what is the particle. Let me see. Oh, this one might be because they lead to the earlier soot oxidation because they already oxidation, so lead to the incomplete combustion later on. Lead to incomplete combustion, so that's why the soot particle might be increased. Because they have the earlier ignition or earlier combustion. Earlier combustion it means what? With lack of the oxygen. Earlier combustion is lack of the oxygen, so that's why.